In today's video, we're going to cover two topics. One is the structures of acids. We're going to look at different ways that we can categorize acids and name them. And then we're going to look at concentration. We know a little bit about molarity from the last series of videos, and now we're going to look at how molarity affects acids and bases. Acids really fall into two broad categories. One is binary acids, and there aren't very many of these. Binary acids contain only hydrogen and one other nonmetal. When we name them, we always start with the word part hydro, and we end with the word part ic, and then we put the word acid at the end. So here's an example of a binary acid. It has only hydrogen and sulfur in it, H2S. We would start with the word hydro, word part hydro, and we'd put sulfur in the middle, and we'd end with ic, hydrosulfuric acid. There's another binary acid, HF. Hydro is how we'd start it, its name. We'd put fluor in it, from fluorine, and then we'd end with ic, hydrofluoric acid. Like I said, there are very few of these things. Some of them are very important. The hydrohalic acids, which are made from halogens, HF, HCl, HBr, HI, are kind of important, but there aren't a whole lot of these. There aren't very many binary acids, but there are thousands of these. Oxyacids. Oxyacids contain hydrogen, oxygen, and some other nonmetal. If that other nonmetal is modeled by X here, we will see that in the Lewis structure we'll always have an H, O, and then whatever that nonmetal is, chain, in the structure somewhere. When you look at oxyacids, like an example is HNO3, you will, if you take the protons off the front, recognize kind of the skeleton of an anion that you probably have seen on your polyatomic ion sheet. If that anion that you see there ends with 8, the name of the acid will end with ic. If the anion ends with ite, the name of the acid will end with us. Here's a little memory device that some of my students invented a few years ago. Ice, skate, mouse, bite. If you can remember that little phrase, it's a nonsense phrase, but it helps you remember this. Ice, skate, mouse, bite has in it ic for 8 and us for ite. Let's practice. H2SO4, if you look at what's left if you take the protons away, it's SO4, which is sulfate. Sulfate ends in 8, and so this acid is sulfuric acid. Now notice that there's no hydro prefix. The difference between H2S and H2SO4 is this is binary, and so it's hydrosulfuric acid, but this is an oxyacid, so it has no hydro in it, it's just sulfuric acid. SO3 was sulfite, so this would be sulfurous acid. HNO3, that's nitrate, so this is nitric acid. HNO2, this anion is nitrite, so this is nitrous acid. Of the oxyacids, a very important group of them are called carboxylic acids, or organic acids. They consist of a backbone of carbon atoms that ends or terminates with a carboxyl group. So this is going to be at the end of all of these kind of acids, and this is the H that splits away that makes this an acid. What's attached here, well, it could be just an H, but most often it's going to be a carbon that could be attached to any number of carbons. So this could be a long chain of carbons here, or a very short chain. And this COOH is often condensed or shortened to COOH when you're just writing out formulas rather than drawing out structures. Here are two important carboxylic acids. This is acetic acid. The word acetic acid, this is not a formal name. It's almost a nickname that most chemists still use, but it's an old name that comes from the Latin word for vinegar, aceto. And this acid, acetic acid, is the acid that makes vinegar taste sour. Acetic acid could be written alternatively as CH3COOH in the condensed form. So here's CH3 and then COOH. This acid is called formic acid. It has no carbon chain, just a single carbon, the one that's part of the carboxyl group. This is sometimes written HCOOH. Formic acid also has an interesting history. The name forma comes from the word for ants in Latin. And formic acid is the acid that stings you if an ant bites you because they inject it into you. In acids and bases, it's the concentration of the H plus and the OH minus that eventually end up in the solution that are the most important to us. They're the ones that you have to consider the most carefully. So the concentrations of H plus and OH minus depend on two things. What is the concentration of the acid or the base that's the source of that H plus or OH minus? And then the second thing is, per unit of acid or base, how many H pluses or OH minuses are released? What do we mean by that? Let's look at some examples. What's the concentration of H plus ions in a 2.00 molar solution of HCl? Well, if I look at what happens to HCl when I put it in water, because it's a strong acid, it splits up completely to give me H plus and Cl minus. Because the stoichiometry is 1-to-1 between HCl and H plus, if I have a 2.00 molar solution of HCl, I will also have a 2.00 molar solution of H plus. This example asks what's the concentration of H plus in a 2.00 molar solution of H2SO4. Well, this is a diprotic acid. So when we see H2SO4 split up, it gives 2 protons and 1 SO4 2-. Now we have a 1-to-2 ratio. So a 2.00 molar solution of H2SO4 actually gives me 4.00 moles of H plus per liter. Here's a base example. NaOH. If I split up NaOH, I've done this one a couple of times already, Na plus OH minus is the result. I have a 1-to-1 ratio between NaOH and OH minus. So if I have a 3.00 molar solution of NaOH, that's also a 3.00 molar solution of OH minus. By contrast, calcium hydroxide, when I split it up, I'm going to get a calcium ion, which has a 2 plus charge, and 2 OH minuses. So again, I see a different stoichiometry than 1-to-1. I have a 1-to-2 ratio. So if I have a 3.00 molar calcium hydroxide solution, I have a 6.00 molar OH minus concentration. There's a really common notation in solution chemistry that's used very often in acid-base concentration, and that is square brackets. Square brackets indicate concentration in molarity unless something else is specified. So a 2.00 molar H plus solution could be written as concentration of H plus in square brackets equals 2.00. Or a 3.15 molar OH minus concentration could be written square brackets OH minus equals 3.15. Well, there's a relationship between how much H plus and how much OH minus can be in a solution at the same time. And that turns out to be a relationship that has a lot of implications in a lot of different areas of chemistry, industrially or in life sciences as well. Next time we're going to talk about the relationship between H plus and OH minus, and we're going to get into something that's called pH that you may have heard of before but maybe don't know what it means yet.